we're going to start with our next unit is going to be our calculus units, which is fun. Calculus to me is where I used to find maths. I was always like meh about maths until I started doing calculus, and I was like, yeah, that's awesome. I love calculus. So what calculus is about, if I write a linear equation, or what calculus is about at the start, if I write a linear equation, what's this? Gradient, right? What calculus really is about at the start is it's all about the gradient of a function, right? If I was to draw for you a function like this, and this graph went between, I don't know, 2, 7 and 3, 13, how would you calculate the gradient of that straight line? Rise over run, right? So there's this equation that you've been having drilled into you since you were probably in year 7, was the first time you've seen it, is that your gradient is equal to rise divided by run, which is equal to, what's the long form formula?
1, 2 minus 1, 1 and x2 minus x1.
Yep. For me, there's absolutely no reason to memorize that formula because it's really obvious if you just remember rise over run. And there is another way that we write this that you might have met in year 10. Those of you who are doing science have probably seen this notation, is that we call this delta y over delta x, right? What does delta mean when we use it in maths and science? Change, right? Delta means change. So what this is just saying is this is my change in my y value divided by my change in my x value. It's just all different variations of rise over run, right? The only one you ever really need to remember is this. If I say to you, find the linear equation or find the rate of change for me between these 2 points, it is just rise over run, right? These are just different variations of that. Okay, but easy to find the gradient of a line when it's a linear equation. What would happen if we had not a linear equation, but a cubic? And what would happen if I said to you, find for me the rate of change between here and here? Sorry? You could. That's one way you could do it. You could draw, because this is no longer a straight line, right? This is a curve. So I could try and draw a linear equation between these 2 points and then calculate the gradient of that linear equation. That is one way I could do it, absolutely. This is what we call an average rate of change. Right? Because it's not necessarily telling us what's happening in the moment, but it's telling us what's happening between the 2 points. What would happen if I said to calculate the average rate of change between here and here? So what would be, oh, maybe I'll put that one a little bit lower, but I think you can see what I was trying to do. What if I told you to find the rate of change between those 2 points? What would be the average rate of change between those 2 points? 0. But has my y value changed between these 2 points? It has, right? If this was the, say, something like the speed of a car, the car's speeding up, the car's staying the same speed very momentarily, the car slows down, the car speeds up again, right? Yes, we're traveling the same speed here and here, but we're doing it in a completely different way, right? So this is called an average rate of change. What calculus focuses on doing is what actually is the gradient at this point. What is the very specific gradient at that point? Can anyone think of a way that we might do that without using calculus? Those of you who already know a little bit of calculus. Katie?
No.
Oh. Another way we might do it, what if I don't draw a point between here and here? What if I was to draw a tangent? Could I draw a tangent at that point that has the same gradient and then find the gradient of that tangent? Might that work? Yeah. Could work, right? These are different techniques that people used to use before calculus was invented, right? So there's different techniques you can use. The good thing about calculus is that it lets us actually find this exact, gradient. So what we need to talk about today, before we actually start getting into any calculus or really any calculations at all, is we just need to talk about rates of change, right? And what a rate of change is. Rates of change. Because you tend to do, in year 7, 8, 9, 10 maths, you tend to do linear equations and you talk about gradients and you talk about all these wonderful things, but you never really talk about the why, right? Until you get into doing physics or chemistry or something like that, you never really talk about the why of why we care about a gradient. So I'm going to draw a graph here. And this graph is going to be a distance, so D for distance, and T for time graph, right? And this is me going to work in the morning. So when I get out of bed and I get in my car, how far away am I from home?
Probably about 20 Ks.
From home, when I get...
That's from school.
Yeah.
Yes, so I start with a distance of 0, right? And then the speed limit on my street is 60. So if I'm doing the speed limit down my street, my distance from home is going to go up like that. And then when I turn the corner, the speed limit's 100. So what happens to my distance away from home once I start doing 100? It's going to keep increasing, right? But the rate that it's increasing is going to go up, right? Now, those of you who know Dumbo, what happens once you start leaving Dumbo? Can you go down that 100 straight?
Lots and lots of turns.
Lots and lots of turns, and there's a really steep hill. So what's going to happen to my distance away from home as I'm going up that big hill? It's probably going to slow down a little bit, right? And then I get onto Narina Road. What's the speed limit once you get onto Narina Road? What's the actual speed that most people do down Narina Road?
100.
Yeah, about 120. So what speed do I do down Narina Road while I'm on camera? Yeah, I'm a nice safe driver, right? So there's a graph. And then school, school might be here, right? So I've hit school. School's about, I think it's about 19.6 Ks from my house, I think. I'll measure it. All right, so here's my graph. I could do this as like a whole bunch of different piecewise linear graphs if I wanted to. I could do a function. I'm not going to bother. It's not worth the effort. But what does the gradient of this equation tell me? So the gradient is, if we think about that notation we went before, my gradient is equal to my rise divided by my run. Remember that notation that I talked about last time with the deltas? Changing y over changing x. But what's my y value? What's my y value represent now? It's got a physical quantity. Distance, right? So this is actually my change in distance divided by my change in time. Who here does physics? What's distance divided by time? Speed, right? So this is my speed. So the gradient of my graph tells me my speed, right? And this is why we care. This is the entire reason why we do this whole subject, is because it's relevant for physics and chemistry and everything else.
Might want to start writing a little further down.
Oh, I'm a little bit, wow. That's bad by me. Wow, that's better. Okay, so if I did a second graph, but now I'm not going to do distance, now I'm going to do speed. And let's do my same thing. So now I've got speed on the y-axis. So when I leave home and I'm driving at 60, I'm driving at a constant speed, right? And then when I turn the corner and the speed limit's 100, I go a little bit quicker. Then when I go up that big windy hill, I might be going a little bit slower again. I might go down to like 40 or 50 or something. And then when I hit the Narina Road again, let's say I'm speeding this time and I'm doing like 130. So my speed versus time graph looks a little bit different. Here's the thing though, when you drive, do you automatically just drive at the same speed the whole time? No. So my graph isn't disconnected like this, is it? I don't automatically go from driving at 60 to driving at 100. There needs to be some kind of point here where I go from driving at 60 to 70 to 80 to 90 to 100, right? So there is actually some kind of gradient here between them. Same as when I start going up the hill. I don't just go from the hill doing up to 100 to go 60. I need to actually decelerate. I need to go down. And then I might do something similar here, right? And even these parts, I might not be doing it like a flat. If this is our 100 section, I might not be, sorry, if this is our 40 or 50 section going up those big hills, it's not going to be a constant speed the whole time. It might actually do something like this, right? So there's going to be some kind of variation in the speed that I'm doing. All right, so let's think about what does a gradient tell me about this? What does the gradient mean for a speed time graph? So my gradient is my change in speed divided by my, that's a really bad triangle, wow. divided by my change in time, which again, someone's already said it. For those who do physics, what's speed divided by time? Nope,
Acceleration.
acceleration. Yeah. So if I have a speed time graph, my gradient represents acceleration, right? If I'm driving at a constant speed, what's my gradient here? Zero. So if I'm driving at a constant speed, what's my acceleration? Zero. Yeah, because I'm not accelerating, I'm not decelerating. When I go from driving at 100 to driving at 60 or 40, whatever it was, what's my gradient in this section here? It's a negative gradient, right? So my acceleration is negative, so my car is slowing down as I go that section, right? So you just need to be aware that there is some kind of physical meaning behind what a gradient is telling us. Yeah, and we can do this for all different kinds of graphs. It doesn't have to be speed and time or distance and time. It could be anything, right? There is literally an infinite number of physical or chemical or biological properties that we can model with this, right? We could do this, usually, actually quite often is time. Time is an important one, but it could be like the population of the bacteria, right? Changes with respect to time. And we'll actually talk a bit about that in term 3, all different kinds of things. Anyway, that's it for me. Go take a 5-minute break because it's almost the end of period 3.